అన్న నువ్వు బయలుదేరన్న, టైం అవుతుంది.
వస్తాను రా.
అన్నా వాకింగ్ స్టైల్ మార్చరాదే, పోరీలు ఉన్నారు.
మళ్ళీ ఏంట్రా?
కాలేజ్ ఇటే.
ఓ మొదటి రోజు కదా, టెన్షన్. వస్తాను రా.
స్టైల్ స్టైల్
అన్న స్టైల్ స్టైల్ అన్న.
Good afternoon, sir.
So I was could not take your test basically because I unfortunately got into the trap of COVID-19. So I was basically in hospital and all. So that is the reason for the delay and stuff like that. So the whole idea is to utilize this week and try to finish some of the major topics on the basic introduction to VLSI design. So I think what all that we have covered, we need to kind of get back to that. And then in addition to that, the whole idea is to finish some of the major topics, after which we shall be having our examination the coming week. So you just let me know the days, and we will be having examination probably next Monday or Tuesday, as you people kind of decide. Apart from this, we shall be having classes today on Thursday and Friday, and I think some of the major topics that have yet to be finished under this VLSI introduction to VLSI design would be taken care of. And if you have any other queries, I think there will be some advanced version of VLSI design courses which I will be taking or somebody else will be taking, and those can be taken up from there. So let's start from what all we have done. I think I will ask Sania Agarwal to kind of recollect and collect whatever we have done till date so that we can proceed further. And I would also request some of you to kind of go through some materials so that we are on the same page. Those who kind of missed it, or some things which I have not talked in detail. And if you have any issues or if you're finding trouble, just let me know. Yeah, Sania, can you do this?
Yes, sir. Sir, you have started with the use of VLSI, like the use of semiconductors, importance of semiconductors. Then you gave us an idea on fabrication of fabrication of VLSI, like CMOS, MOS circuits, like etching and all the fabrication, all the process that a chip goes through before like converting into CMOS, and different properties like so we all in the last classes we were talking about the CMOS and building different gates using CMOS technology, like XOR gate, NOR gates, NAND gates. You discussed about those things, and you were talking about NAND gates, creating NAND gate, NOR gate using CMOS. Other than that, you talked about the properties like channel length modulation and velocity saturation.
So basically we also talked about what is generally happening. It is the scaling of your transistors, which has allowed us to have more and more number of transistors per unit area, and that has essentially helped in to have more sequential and combinational circuits within the same chip area. So like if 10 years or 20 years or 30 years 1 cross 1 centimeter would have certain number of logical gates, out of which a kind of module, a sequential circuit module or a combination circuit module could be captured in that area. Now, because of simply squeezing the transistors, which was governed by Moore's law, we were able to have more and more number of transistors. That means more and more number of combination sequential circuits and up the order. But as we continue to scale down the transistors, these were the so-called short channel effects that came into picture, which needed to be avoided. Something like, as we've already talked about, drain-induced barrier lowering and the other short channel effects that had emerged when the transistor size entered into the submicron level. So like 0.18 or 180 nanometer or 0.18 micron technology or 0.13 micron technology, you had all these short channel effects which came into being, and one had to kind of overcome these challenges, because otherwise the device performance would go down and the circuit performance would go down. So that would basically hijack the performance of your any analog or digital circuits. So that was what we said. So I think, yeah, Sanya, can you carry on? What else did we do? So short channel effects is also part and parcel of your examination. I think these are like very fundamentals and basic. And then you see these transistors has been modified into these next generations SOI technology, and which is silicon on insulator and FinFET based technologies, and the scaling has continued beyond 130 nanometer, which is 0.13 micron. So from micron level, it came down to nano level, which is like 90 nanometers, 65 nanometers, 45 nanometers, so on and so forth. So all these challenges which are coming out of the transistor performance, which are deteriorating the overall effects of the, whether you talk of combination circuits or sequential circuits, these are the performance degrades basically because of these device performance, mainly due to the short channel effects. And so the modified version in terms of material, in terms of geometry, in terms of design, all these have been changed. And so nowadays in the industry, majorly people are talking, they are doing a mass production of few tens of nanometer, and that is around 22 nanometer or 32 nanometer. So that is the mass scale production. All the chips, whatever you're using, whether you're talking in medical electronics, like even if you talk, there would be a chip in the instrument that you use to detect the pulse rate, or the oximeter that a lot of you may have bought it nowadays. So if it is a digital oximeter, which is most of the times, you are having all these chips. And whether you're talking about automobile industry or whether you talk of anything and everything on earth, so that is why we were these chips and sensors and memories and processors in this internet of things. And that is why it is called all internet of everything. So that is becoming smaller, better in terms of performance. So you need to have smaller, cheaper, better in performance, having lesser amount of power that is needed to run such kind of circuits, so on and so forth. So that is that is what we have talked in detail about short channel effects. Yes. So what else, Sanya? And you also said about like how to make the basic universal gates. I think I will just try to extend that So when we said that universal gates, it is essentially the NOT gate, the NAND gate, and the what are the three universal gates? Out of
NAND
which
nor not.
NAND, NOR, and NOT.
Yes, sir.
So that is how it build up. But any kind of gates, any gates. So let's talk of why did we start with this Boolean algebra in our digital logic or digital electronics course. So like you take any Boolean expression, you can express that in terms of CMOS. Let's take an example, and I think that will also be a part and parcel of your exam. So that you are able to understand that any circuit that you talk about, everything can be expressed in terms of your CMOS ultimately would narrow down to a CMOS based technology. So Sanya or let's talk about Dhirendra. Give me any expression. Dhirendra, are you there? Dhirendra, Navratan, am I audible? Navratan, Aniket, Aniket. Okay, I think I will not be calling out names. It's better. Sanya, can you just continue? I mean, like, can you give us any expression? And this is for all of you. Please write down any Boolean expression. Hello.
So like we have two, like if we have two inputs, like we can A plus B.
Just write any arbitrary,
Okay.
any expression. Yeah, yeah. Just put it on the board so that everybody can see. And then all of you try to solve it or identify it using the CMOS technology. So I think it is the extension of your NOT gate, NAND gate, and the
Sir,
third.
sir,
Yeah.
haven't we already done this though?
So you can you know how to have any kind of Boolean expression being expressed in terms of CMOS technology.
Yes, sir.
Okay, okay. Then I think yeah. Can we go further? What all we have done? Yeah, that is. Then you've done what else? What all you've done? You've done scaling. You've done this thing. So I think then we should just go to the uh, basic characteristics of the inverter. Have we done that?
The characteristic in the sense like everyone got. So you talked about CMOS and like, but not specifically characteristic of the inverter. Like we have
First of all,
simply use a NAND. We have created NAND gate and NOR gate using CMOS. You discussed how it works and the like flow of the CMOS.
okay, right now also you can do you have this expression. Take any expression, say like y, any Boolean expression. Y is equal to ABC plus B, AC plus BD, D bar C bar plus. You write any. Yeah, Ishan, you give one expression. I think it will just take 5 minutes.
Sir, A and B.
Like, can you be louder? I mean, like so that everybody
Sir,
notes
A,
down.
just an A or B,
No, no, no.
whole
I'm
ANDed with
asking
C.
you. First of all, you just give any generalized bit, a bit complicated Boolean expression. If you cannot do, I can do, and then just any arbitrary. The whole idea is like, how do you solve? First of all, what was the point of doing Boolean expression, and then how do you actually realize it using CMOS? Because at the end of the day, any kind of combination sequential circuit is done on CMOS, right? So that is the reason I'm asking you to try it. Yes.
Sir, I'll just write it in chat.
Not you, I mean the whole class. I need the whole class to be getting involved. Hello? Okay, please write it down. You just take y is equal to a b bar c plus b bar c bar d bar plus a b bar c d bar plus a bar b c plus a b and e. Can you solve this and let me know how many transistors would be required?
Sir, could you please repeat, like just to check?
I forgot. Somebody
Okay.
else can repeat. I just gave any arbitrary one.
Yes.
Siddharth, can you repeat? Ishan, can you repeat?
Sir, actually, I couldn't note the entire thing out. I'm waiting for someone else to repeat it.
Okay, okay. You just say to the point you have been able to note it down. Sanya?
B bar C or D bar B bar C bar. That is all I could get.
Okay, I repeat once more. I mean, like, scratch A, B, C bar, D, then B, C bar, D bar, plus A, B bar, C bar, plus A bar, B, E. Okay, so can you just solve this and then express it in terms of CMOS? And there will be a question based on this in your exam.
Sir, I think you forgot to say an expression between the first two
That is
terms.
also plus, yeah. Some of the products. Sanya, would you like to repeat the question once again?
Okay, sir. Sir, like A, B, C bar, D plus B, C bar, D bar plus A, B bar, C bar plus A bar, B, E. Is that right? Like,
Yeah, I
can you
think
can
that.
confirm?
Yeah.
Yes, sir.
So this is any arbitrary logical expression in Boolean expression form. So at the end of the day, what you want to do is to get the same output with minimum number of gates. So when you are talking about gates, you have to connect it with transistors, and the transistors that we all know, the basic block or the building block always happens to be a CMOS, as we have seen in the case of NAND and NOR. So is any kind of expression. Anything and everything can be expressed in terms of CMOS. That's the key point. That's why we are taking this as an example, and it will be also part and parcel of your examination. So that's why I'm giving you 5 minutes. Just try to solve it and then realize it using the CMOS pattern. So again, like in NAND and NOR gate, you have to now express this Boolean expression in terms of PMOS and NMOS transistors, knowing the basic characteristics of PMOS and NMOS, and you have to basically get it in parallel or series combination of PMOS and NMOS of the expression that we have chosen right now. So first you need to solve this expression so that you have minimum gates, and then the second part would constitute of expressing it in PMOS and NMOS, essentially CMOS. We have not done CMOS inverted as a voltage transfer characteristics, right?
No, sir. We haven't.
No, sir, we haven't.
Finished? Can I ask you one more thing? Have we also talked about the constant field scaling and constant voltage scaling before? So there will be some.
Yes, sir. We have talked about.
So there will be numericals based on that.
Yes, sir.
And then you have the so-called generalized scaling, in which you have best of both worlds, so as to say.
Yes, sir.
So I think we would like to finish with the CMOS inverter basics, as well as some of the other important things like the power analysis and stuff like that. So I think that would take another couple of lectures. So that basics of CMOS, so basics of inverters, and from which inverter is basically CMOS. And since you can express any kind of combination or a sequential circuits as a Boolean expression, or in a repetitive mode of blocks of these combination or sequential circuits, you would have overall idea about the basics of digital IC design or digital VLSI design, and you can build up upon that. So if you have the basic knowledge, then if you want to make, say, 16x16 multiplier or a subtractor or any kind of even sequential circuits going up to right from latches to your counters to up the ladder you would be able to realize using the CMOS technology. Similarly, we will be just brushing with the difference of using the same CMOS technology in analog, and we will see in particular about how it is more powerful to use the CMOS based technology as a switch. So have you finished? If someone has finished, kindly display his or her results. Hello. Navratan, Manas, Manali. And then I think on the final day, we will be also talking about a little bit introduction to your hardware description language. So that, you know, when you're talking about the real design, you are doing it on some HDL. And I think in the future courses, if those who are taking those courses, we will be actually doing hands-on on things like synopsis, or if we are able to, so synopsis is already there in your school. There is another very famous industry based tool which is Cadence. So these two things are largely used in the so-called VLSI industry, semiconductor industry, which is from Apple to Samsung to any electronic industry, whether it's in medical electronics or even in automobiles. So remember, the automobile industry is gradually shifting towards electrical and electronics. So the power generation is mostly electrical, and the other thing is electronics. It's completely shifting from the so-called gasoline based to electric. So in the near future, as in like when you graduate or a few years down, you will have more and more of these electric vehicles all over the place, not only in outside India, but also in India, where you will be having all these. Similarly for robotics, I mean, it's all about processes and signal processing, and which is basically designing of these chips. So if the chips are not there, it's complete handicap for any of these AI or cloud or anything that is working. So that is the starting point. The other important thing is like traditionally, even in medical electronics, where CAT scan, MRI scan, everywhere they are having all these electronic chips, which is helping you to navigate and scan your body parts and helping you to diagnose all kind of ailments. Have you finished? Anybody? Manas, Navratan, Sai Vikas, Manali.
So I've put my output in the chat box.
Can you just show so that we can also try to figure
So
out?
my system is facing issues. I like
Okay,
won't work.
anybody else? I mean, like it's not. That's okay. Is it? So this is that you solved. Now, how do you realize it using the CMOS technology? So like just take the clue from the expression that you get from a NAND gate. That is also a Boolean expression. So in that NAND gate, what is the expression for NAND gate? Boolean expression? Sanya? Sanya? Manali?
So A dot B whole bar, like if
A dot B.
whole bar, like or A bar plus B bar.
Okay, so now you're having this as an expression. So that you could simply realize by having PMOS in parallel or series. The NAND gate. Hello, Sanya. Sanya, am I audible?
Yes, sir, you're audible. Like my system got
Yeah.
hang.
So this NAND gate that we are talking about
Yes, sir.
is realized by CMOS in what manner? The
So
PMOS
like,
are in what? Parallel or series? And NMOS
so
are in, yeah.
NMOS are in series and PMOS are in parallel in CMOS. Like if in CMOS.
So you have two inputs, say A and B, and it
Yes.
is product of these two inputs with a bar, right?
Yes.
So now here you're having this expression. You have solved the complete expression and you have got this expression. So here you are having A dot C bar plus A bar B dot C dot D plus A bar B dot E. Now can you realize the whole in terms of CMOS technology? The answer is yes. And the Q is your previous knowledge. What is the previous knowledge that we are talking about? The PMOS, the characteristics of PMOS and NMOS, and how with the kind of combinational circuit, how with the NAND gate and NOR gate, we were able to express this Boolean expression, which is A dot B and A plus B. Okay. So since you could express both NAND gate and NOR gate in terms of CMOS technology, even this expression that you've been able to solve can be expressed in terms of the CMOS technology, where you will be using different types of series and parallel combination of PMOS as well as series and parallel combination of NMOS. And then you will see the output would be the same. Any volunteers? Manali, Sanya, Manas? The same expression, A, C bar. So remember, for anything which is okay, let's do it. Let's try to do it here itself. So you bifurcate it into the PMOS part and the NMOS part, and wherever you have the product, you relate with NAND, and wherever you have addition, you relate with NOR. So like in the NAND gate case, you had A dot B. So in A dot B, your PMOS was in parallel. So in this, A dot C would be in parallel, while your NMOS would be in series, like in the case of NAND gate. And in NOR gate, if you had A plus B, the PMOS was in series, while your NMOS was in parallel. Sanya, Ishan, Navratan? Hello?
Yes, sir.
Did you get what I said?
Yes, sir.
So can you just do it? Premlata? Yeah, show it to us. This is very important. Actually, we are trying to build up for any circuits. So any circuits can be realized from the building block, which is your CMOS transistor. And why are we talking? Why would we? Why will we talking about the CMOS inverter in detail? Is because in digital electronics, everything is made up of CMOS. Like we would be seeing from this kind of Boolean expression. If this Boolean expression can be expressed in terms of CMOS, any Boolean expression can be. That means any kind of combination circuit or a sequential circuit can be expressed in terms of your CMOS technology. So we should be knowing in detail about the CMOS technology. That is why we will be going to the voltage transfer characteristics in a subsequent talk. But before that, we should be able to express this expression, this random Boolean expression in terms of the CMOS technology. Taking a cue both from the properties of PMOS and NMOS, as well as taking the cue from expressing NAND gate and NOR gate in terms of NAND gate and NOR gate in terms of CMOS technology. So once we know that, everything can be done. Then whatever knowledge we can gain as a CMOS can be replicated for any kind of Boolean expression. That means any kind of complicated circuit. That circuit can be a combination circuit or a sequential circuit. Analog world is different. Please, hello. Let me know whether you have finished or not. Hello. It's 2:40. Should we proceed further?
Yes, sir.
So can you, Navratan, please show. Can you scan and show to us?
Sir, my camera is not that good.
Okay, then let's proceed further. Okay, can you see the slide? Hello?
Yes, sir.
Yeah.
Yes, sir.
Okay, fine. So I think this I am sharing from Dr. Buddhi, uh, Dr. Sudev Dasgupta from IT Roorkee, and I think we are extending on the CMOS inverter part, its basic idea and the basic knowledge, because CMOS inverter happens to be the fundamental block out of which you can express or realize NAND gate, NOR gate, as well as any kind of a Boolean expression. So whatever characteristics we will be studying that would translate and grow for any kind of combination or sequential circuits. So the basic knowledge of CMOS inverter is very, very important. So in the CMOS inverter, they basically since we are dedicated more towards the digital IC design or the VLSI design, which uses millions and billions of transistors, as we have seen before in classes like your microprocessor, or for memories like SRAM cell or a DRAM cell. We shall be talking in detail about how does a transistor acts as a switch. So remember the basic difference between the working of transistor and its region of operation in transistor basically translates and regulates whether the transistor is going to be used for analog application, analog circuit application, or digital circuit. But since your VLSI is focused more towards digital side, we shall be talking about the CMOS inverter as a switch. So the switch model of the inverter would be talked about in our subsequent slides. Its static behavior. So we will be talking about what exactly is the static behavior, the voltage transfer characteristics, the switching threshold that would be determined from the voltage transfer characteristics of your inverter, and would give you the noise margin. The gain calculation is a parameter which we shall not be discussing, and it relates more towards the transistor operation in the linear region, where you determine it for your analog circuit application. Remember, the transistor that we are talking about is for digital application. So digital basically means 0 and 1 only. So 0 is the cutoff region, while 1 basically is your non-linear. And there is another important parameter which is gain, that is for your analog application. Okay, so gain is delta V out by delta V. And some of the other important parameters that one needs to determine in the CMOS transistor or in the transistor itself relates to the transconductance. So we shall not be touching on those lines. So the CMOS transistor we have already talked about. We shall again try to brush up few things. So how does it operate? This is how an inverter looks like, a static inverter. So what do you see? You have input B in, you have output B out, and you have the PMOS on the top and the NMOS at the bottom. So in this configuration, you have the transistors, which is PMOS, where your source is connected to your VDD and the drain is common to the output as well as the NMOS, which is at the bottom, which is transistor M1 here, and the source is grounded. So here you have the output capacitance which gets loaded when the voltage at VDD is directly connected to your Vout. That depends on the characteristics of your PMOS transistor and your NMOS transistor. So PMOS transistors conduct when the gate voltage becomes greater than your gate voltage becomes 0, right? For which transistor? Hello? Navratan?
Yes, sir.
Yeah. So when will this PMOS conduct? When will this PMOS conduct? Manali? When does this PMOS conduct? Manali? Are you there?
Yes.
Yeah, when does this PMOS conduct?
When it's biased.
I'm not able to hear you. Hello?
Yes, sir.
Yeah, when does this PMOS conduct?
When it will be biased, then its conducting will start.
Your voice is not clear. Sanya? Sanya? Are you there or not? Sanya? Manali? Am I audible? I'm getting no response.
Yes, you're audible.
Okay, so I continue if you're not able to trace out. So when the gate voltage
Sir,
V
Sir,
yeah,
the PMOS will be on when the input is low.
yeah, input where?
Sir,
At the
Vn
gate.
in this figure. At the
At
gate,
the,
yeah. The VGS,
at, Yeah. So at the gate is low. So that means here this is transistor M1 and this is transistor M2. So M2 is your PMOS transistor and M1 is your NMOS transistor. So when N2 is at the gate of N2, which is Vin, is going towards low or is low. Low basically means touching zero. Then there will be a direct connection between your VDD and Vout. And so your load capacitance CL here will start getting charged up. While the NMOS transistor in the same condition, which is when your Vin, which is basically translating into the zero voltage in your transistor M1, the gate of transistor M1, that forces this transistor to go into the cutoff stage. So there will be a direct connection between VDD and Vout when your Vin is at zero or close to zero, because this transistor will be in on state. At the same time, this transistor will be in the off state. Now, as there is a transition from at the gate of the two transistors, which is PMOS and NMOS transistors, which is Vn going from state 0 to state 1, the reversal will happen. That will force the transistor PMOS to go in the cutoff stage, while force the NMOS transistor, which is M1 at the bottom, go into the conducting state. So when Vin becomes equal to 1, that basically means that the gate of M2, which is a PMOS, goes high, then this transistor will be cut off state, that will cut off the voltage VDD to your Vout, and it will stop charging. While whatever is here at this stage, at the same time, when your Vin is in the high state, this transistor M1, which is an NMOS transistor, will start conducting. So whatever voltage it has, since your source of your NMOS is grounded, would force to come in the ground state, because NMOS transistor is in the conducting state. So there will be a complete discharge of the capacitor C load, which is at the output of your inverter. So this is why when you have input as 0, the output becomes 1, because whatever voltage VDD is there comes as a Vout, and your capacitor CL gets charged to up to VDD. While when your Vin is in state 1, then this transistor is in the cutoff state, so there is no flow of current or charges from VDD to Vout, and but there is a flow from Vout to your ground. So it forces the voltage here to go into the ground state, and the load capacitance CL gets discharged. So when your Vin is 1, the output becomes 0. And in between the two, there is a transition period. And that is what we shall be studying in detail in the subsequent class. Is that clear? Hello? Hello? Are you still around? Navratan?
Yes, sir.
Okay. So I think I've given you some idea about the CMOS inverter. So this Vin happens to be the voltage that you give to the gates of your PMOS transistor and your NMOS transistor. And the transition happens from 0 to 1 or from 1 to 0. And simultaneously the output is from 1 to 0 and 0 to 1. So here we shall be talking about the transistor only in the cutoff state or the saturation state. So the idea is to talk about the CMOS inverter and correlate it with the so-called switch model. So you can imagine the PMOS as a simple resistor or acting as a switch when your NMOS is in on state while PMOS is in the off state, and the gate voltage Vin is equal to VDD. So there it is acting as a, your PMOS is acting as a switch while your NMOS is acting as a resistor. Similarly, when your Vin, which is the